Okay, so this week we're going to be looking at vectors. We're going to start out looking at 2D vectors. On Thursday we'll do a little bit in 3D. Okay. So has anyone studied vectors before or already familiar with what vectors are? No. Okay. So vectors can be represented a couple different ways. One way is visually. Okay, we'll do a lot visually today. We can also represent vectors just using numbers. Using numbers is more efficient, it's faster. If you have to draw things out every single time you want to do something with vectors, drawing takes a while. Drawing is good for word problems because you kind of need to see what's going on. But if we can avoid drawing, like tomorrow and Wednesday, we will. Okay, so basically a vector is a quantity that represents two things at the same time. It represents a magnitude and a direction. So what would be an example of this? Let's say that you wanted to describe an object moving. If you wanted to describe an object that was in motion, what's one thing you would have to describe about it in order to describe exactly how it's moving? Yeah?
Like the velocity of it?
So, and what do you mean by velocity?
Like meters per second, like in that direction.
Okay, so the speed of it and the direction of it. Yes, those would be the two things. And that's one example that we can use a vector for, velocity. Remember, velocity has two parts to it. How fast is it going? That's called the magnitude. And what direction is it going in? Another example would be like a force, right? A force has two components to it. Like how hard are you like pushing or pulling on something, and the direction. There's a difference between pulling upward with force or pulling downward. Okay? The direction is different. So a vector can represent both of those things at the same time, the magnitude and the direction. So one way we can represent a vector is with an arrow. Okay, if we're going to draw it, that's generally how you do it. What do you think I can change about the arrow to represent magnitude? Yeah?
The side of it?
The side of it. Yep. So these two vectors have the exact same direction, but one of them is longer than the other, which means if it's a velocity, the bottom one is going faster, or if it's a force, it's stronger. So the length of the arrow indicates the magnitude, and the direction that it's pointing, well, that's the direction. So it's kind of like a ray from geometry, but the difference with a ray is a ray goes on forever. Vectors do not. If a vector went on forever, then that would represent something going infinitely fast or an infinitely strong force. That doesn't make sense. Okay, so vectors definitely start and stop at two different points. So those 2 points where the vector starts and stops, we usually call them the initial and the terminal point. Initial is where the point would start, and terminal is where it would stop. Yes.
So even for things that are constantly moving, you could like technically do the initial point and terminal point for like certain periods of time, like to figure out the velocity. Like for if somebody throws a baseball really fast, and you want to like figure out how fast it's going, couldn't you technically like chart where it is like on a graph or something? Like at 1 second it's here, at 3 seconds it's here, and then like use the P and Q like that, or
Well, no, the vector isn't representing position. It's representing speed and direction.
But isn't that position?
Not when you draw an arrow, no.
Alright.
The vector itself does not represent any type of position where the object is. It represents the direction it's going, and it represents the speed at which it's going. So there's a couple different ways that we can name vectors. One way you might see is a letter with an arrow on top of it. This arrow on top is just a generic arrow that points to the right. When you put an arrow on top of a letter, it means it's a vector. The reason we don't just use a letter by itself is because we already use letters in math as variables. And a vector is not a variable, it's a vector. So if you want to use a letter, we got to make it a little different. We can either put an arrow on top, or what you're going to see in the book that I'm going to use, most of the time it's bold. So when you see a bold letter, that is the name of a vector. And you can name a vector any letter, well, mostly any letter you want. Don't use I, J, or K. Those are special. We're going to talk about those tomorrow. But I wouldn't use the letter 0, because that could look like the number, like, I wouldn't use the letter O, because that could look like a 0. But other than that, you can use pretty much any letter to name a vector. Yes?
Like, I understand what direction is, like up, down, left, right, but how does that not indicate position? Like, if you have, like, wouldn't you technically be using this to, like, show, like, a baseball?
It represents the direction of force.
Yeah, but how's that not position?
Well, because it doesn't show you relative to anything else, it's showing you where the force is pushing.
Like if I just draw an arrow and you said, here's a baseball moving through the stadium, all I could tell you is that's the direction of the ball's moving, and that's the speed the ball's moving. I don't know where in the stadium it is. Is it in the outfield? Is it in the stands?
So we're not going to be given, like, an image? Because, like, I remember for triangle stuff, we're given, like, an image of, like, the flag post and, like, the distance from you to the flag post and the...
We will have word problems where we do need to draw it out, yes. Yep.
But we still won't be given the position.
Well, you can tell you that.
Not specifically for a velocity vector,
Oh.
because velocity doesn't indicate position. It indicates speed and direction. But where that speed and direction, where it is, like, is it here moving at 35 miles an hour? Is it here moving at 35 miles an hour? We don't know. Yes?
Can you repeat the letters I can't be vectors?
We don't want to use an I, a J, and a K.
Okay, thank you.
You'll see why tomorrow. Okay, so let's visualize what happens when we add two vectors together. Here's a vector. Here's another vector. I'm going to add these together visually, and I want you to kind of see what happens. If I want to add these visually, what I do is I line them up, just like that. And then I connect where I started to where I finished. That is the answer if you combine the black and the red vector together. I'll just make it a new color to get the green one. What is that green thing that I just drew?
The average direction.
Kind of thinking of like a single word. It's a, yeah?
Oh, I was thinking like the new terminal point should be the new terminal.
So the new what, yeah?
Oh, these, I don't know, it kind of looks like the hook mountains with like triangle.
Okay, so it's kind of like connecting the diagonal, but it's, anyone else have another thought? It's a, what is this? It's a, yeah?
Slope.
Well, there is a direction to it. Yeah.
Vector.
It's a vector, right? That's a new vector. So the point is, when you take a vector and you add it to another vector, you get a new vector. Possibly a different length. In this case, definitely a different length than both of the original ones. And it can also point in a different direction. Because when you're combining the two together, they interact and produce a new force, a new direction. Okay, so that's important to understand. that a vector plus a vector is a new vector.
But is that like for one object, right? Like if we were thinking about it, like realistically, that'd just be one object, right? Not
So I guess like an easy way to think about it is like if you had, let's say you had like a boat, right? Little like floating on like a little pool, and you took a fan and you blew it on the boat and aimed it in that direction, and then you put another fan blowing on the boat in that direction. What direction would the boat move? The boat would move in the direction of the green line,
Okay.
and if you wanted to know how fast the boat is moving, you'd find the length of that green line.
Okay.
So it's like two forces kind of combining together.
Kind of unrelated, was this related in any way to like computer, like WASDA, or like the joysticks for like controllers, where you can technically like cancel out like movement and direction and everything? Like technically for like WASDA, if you hold the W and the A, technically that makes you go this way diagonal because you're only given up, down, left, right. So technically it's not like related to game controls. It's like finding new directions for the given.
Yeah, I guess it could be. It's two things kind of at the same time. Yeah. So let me give you another example. Kind of already shown you the general concept. But let's say you had a vector like this, and you want to combine it with a vector that goes like that. And you want to know what's going to happen when those combine together. Well, what you do is you line up the vectors so that the end of one and the beginning of the other one are at the same point, just like that. And then you draw in from where you started to where you finished. So the result of combining this vector with that vector is that vector. That's how you add them. Okay. I'll write down everything I just did. That's the idea. So I'm calling the two vectors I'm using V and W. So you're going to position the two vectors. Let's call that V and W. Position the two vectors so that the ending of V, that's right there, and the starting point of W, that's right there, line up. So just like that. So the end of one lines up with the beginning of the other. Whichever two, which one did I have originally? Oh, I think it was these two.
Yeah.
Yeah, position them like that. And then you're going to connect the start of V to the end of W. So connect a vector from the initial point of V to the ending point of W. It's kind of like drawing like a diagonal. It's basically what it is. It's actually like the diagonal of a parallelogram. If you, I don't usually draw the whole parallelogram, but if you did, you could kind of imagine like another one over here, and then another one down here, and then you're drawing in the diagonal of a parallelogram. That's really what you're doing. Again, I don't draw the whole parallelogram. Okay, so drawing is good. I think if you're doing a word problem, it kind of helps you to visualize what's happening. But in general, if we really want to just add and subtract vectors, there's a way we can do it with just numbers. Okay, and I'll start to show you that at the end of class. Okay, so let's add these two up. So they want us to do V plus W. Again, these vectors do not indicate position. So you can put V wherever you want. Put it here, put it here. That's not what these are indicating. It's not position. Just put it on your grid somewhere where you're going to have enough room. Don't put it over there. You're not going to have enough space to to do what you need to do. Okay, so I'm going to put V right there. And now, how would I put W on that? Anybody tell me, what would I line up? Yep.
Oh, you just have to align the initial with an endpoint.
Yep, align an initial point with an endpoint.
I'd do like the initial of W to the terminal point of V.
Yeah, this is the initial for W. That's the terminal for V. Terminal is always where the arrowhead is. Let's line them up just like that. Good enough. Okay, so we lined them up. And now how do we get the final answer? Yep.
A squared plus B squared equals C squared.
What's that?
To find the distance between that point and that point, you can just like do the distance, like the x distance between the first and second point, and then the y distance between the first and second point, and then make the triangle to find the hypotenuse or the distance between them.
Okay, so first question, what are the directions asking us to do?
To draw. To add them.
To add V plus W. And when you add V plus W together, you're going to get what? What kind of
vector.
Answer? A new vector. Pythagorean theorem is not used to find vectors.
No, like the distance.
Well, two things. Is it asking for the distance?
No.
No. It's asking you to basically draw V plus W. Now, the other thing is, what kind of triangles can you use Pythagorean theorem on? Yeah?
Right.
Right triangles. So if we were asking for the magnitude of the vector, which we are going to, not now, Pythagorean theorem would not allow us to find it.
But like.
Not with like calling this A and B. But we'll get to that.
No, like I mean, just like the first point is like this part of the triangle, like the top, and then that point's like the bottom, and so you like connect it like that, and so you're given this and this on the grid, and so you calculate the hypotenuse, and that is a right triangle.
Yeah, so if you do draw it, yeah, you could make it a right triangle.
But currently, right now is.
Right now it is, yeah.
There's
So,
an equation that
What do they ask? So let's finish up what they're asking us to do here.
Draw the point from the initial to the terminal. Initial of A to terminal. Okay. Initial of V to terminal of W.
So the initial point of V,
Terminal of W.
the terminal of W, and that is the answer that they're looking for. Okay, so for now they are looking for a visual. That's what they want. Any questions on that? Okay. All right, before we add these, is there any thought what's going to happen when you combine those vectors together? Yeah?
They just cancel.
Right. Because if you want to imagine what we're going to do, we're going to put W on the end of V. So we're going to take where V ends, we're going to take where W starts, and we're going to line those red dots up. That's how we have to do it. Once we line up the red dots, we're going to connect where V started to where W finishes. Okay, so don't worry about connecting the green dots till you line the red ones up first. So let's line the red ones up. And now we're going to connect the green dots. But the green dots are at the same point. So they do cancel out. But what kind of answer do we always get when we add vectors together?
Line.
We get a new vector. So you do have to write your answer as a vector. There's no way to draw it, but there is a way to represent it. That's how you represent it. It's called the zero vector. Basically a bold zero, or you could do it like this. A zero with a line above it. A ray above it.
Wouldn't you want to draw the line through the zero to make sure there's no way, like nobody can see that as O vector?
I haven't seen that notation in our book. I've
line
only
through it?
seen it as a bold or that. I haven't seen it with the line. I guess you could, but I just haven't seen that.
like it's not, yeah, it's not a thing that's professionally used, but like, you know, having a dash on your 7 or the line 3 to 0, like to make sure all the numbers like distinct.
All right, so commutative and associative. What does commutative mean?
Multiply and add. Commutative for multiply and associative for like add. Like,
Well, this is specifically addition. Yeah. So what does it mean if you apply the commutative property to addition? Yeah.
I think it's A plus B equals B plus A, something like that.
Yeah. So you can change the order. You add two things in, and you will get the same result. That works with numbers. It also works with vectors. Okay, let me show you. All right. So here's V and W. Okay, I'm going to take and do V plus W first. So start with V. Put W on the end, and let's draw final answer. Okay. That's V plus W. Now, let me do it the other way. I'm going to start with W, and I'm going to put V on the end of it. Okay, so I'm adding the two vectors in a different order. All right, let me draw the answer, and let me compare that to what we just did. A little off, but you can see it's the same. So when you switch the order, you add vectors in, you will get the same answer. And I'm doing it with two vectors, but you can do this with as many vectors as you have. Right? So you have one like that, one like that, one like that, and one like that. And you want to know what would happen if you combine all those vectors together. You can add them up in any order. As long as you're always connecting the end of one to the beginning of the next. And the final answer for that would be to connect here to here. All right, now let me switch it around. Let me write down how I did it first. So I did green, red, blue, black. So let's just do it in a different order. Let's do red, let's do black, let's do blue, and then let's do green. Let me connect where I started, which was right here. Oops. I started here, I stopped here. Let's see if that purple vector still fits. No, same thing. Okay. So vector addition is commutative. Any order you want to add it in. What does associative mean? Anybody remember that one? Yeah? You can change the grouping. So the order is exactly the same on both sides. ABC, ABC. What I'm changing is what I do first. Okay, that works with numbers, also works with vectors. All right, so to show associative property, I need three vectors. So let me start with what's on the left. Let me do A plus B, and then I'll add C onto the end. Okay, so here's A plus B. And you know what? I'm just going to change this a little because I don't want it to be exactly horizontal. It'll mess me up. All right, so I got A plus B, and that's going to give me that. Okay, so let's put that off to the side. And now put C on the end of what we just did. The vectors are different thicknesses, so might throw it off a little bit. Okay, and we get something. I'm just going to draw right to the middle of the arrowhead the best I can. Oops. Okay, so that's the answer. Doing it the left way. All right, let's put everything back. Don't need that. And now let's do it the right way. Well, the way that's on the right side of the equal sign. let's do b plus c. So here's b plus c. Let's put that there. Okay, connect that. Okay. So now I'm done with those. And now take a and put b plus c on the end of it. Here's a. Let's put b plus c on the end of it. Draw your arrow, and let's compare it to what we just did. Not like that. You can see, well, it's pretty close. I probably messed up a little bit. I didn't put that right on the tip. So it's probably supposed to be a little bit longer than it was. Yeah, a little longer. But you get the idea. Okay, so you can switch the order that you add vectors in, and you will get the same answer. You can change the grouping that you add vectors in, and you will get the same answer. All right, so what do you think the difference is between these two vectors? Vector v, and then putting a negative in front of a vector. What do you think a negative does to a vector? Yeah?
Direction.
How do you think it would change the direction?
I'd say, what? Let's say, positive v is to the right, so I say the negative would be to the left.
Okay, so if positive v was to the right, negative v would be to the left. Can anybody generalize that?
The opposite?
Can you detail a little more what you mean by opposite?
Opposite of v. So like if one's going, so if v that's positive is going one direction, negative v would go to the opposite direction.
Okay, so yeah, it is the opposite direction, yeah. I'm just trying to think of another way we could say it in case anyone doesn't know what we mean by opposite. But yeah, it is the opposite.
You switch your initial and terminal points.
Yeah, that's a very concrete way to say it. The initial and the terminal points switch. In other words, it's like a 180-degree rotation. Okay, it points exactly in the opposite direction. What about the length of the vector when you put a negative in front of it? What would the negative do to the length?
It would keep it the same.
It would keep it exactly the same. Yep. So v and negative v have exactly the same magnitude. They just point in opposite directions. Okay, so what would you get if you add those two vectors together? If you combine v with negative v, yeah?
0.
You would get the 0 vector, exactly. The way I have it written on the board right there, that's technically not right. Now it is. And we saw an example of that earlier. Okay, we did a visual where the two vectors were pointing exactly in the opposite direction, and they canceled out. Anything that's not moving is pretty much represented by this situation. It means there's a net balance of all the forces and it's 0, right? Like a tug of war. If you're pulling exactly with the same force on each side, the net result is 0. Nothing happens. When forces start to become unbalanced, that's when things move. So we can use this idea right here to subtract two vectors. The way we're going to subtract two vectors is pretty much the same way we did addition. How could you think of that problem as an addition problem? Let's say you try to explain how to do subtraction, but somebody doesn't know what subtraction means. They only understand addition. So how would you reword that as an addition problem? Yep.
3 plus negative 2.
Right. 3 plus the opposite of the second number. And that's exactly how we're going to subtract vectors. In order to subtract two vectors, you're going to take the second one, you're going to find the opposite of it, and then you're going to add it. So to do subtraction, we'll find the opposite of the second vector, and then we'll add. So if that's how we're going to handle subtraction, what kind of answer do you think I'm going to get when I take a vector and subtract another vector? We know what happens when we add a vector to a vector. How about when we subtract? Yeah? Yeah, we're going to get another new vector. Exactly. Because subtraction is the same thing as addition. Just addition with the opposite. Yep. All right. So let's see if we can do v minus w. Okay. First thing is, instead of thinking of it as v minus w, how are we going to think of that?
V plus negative
V plus negative w. So that's the first thing we need. We need to get negative w. All right. So since the initial and terminal point are just going to switch, you can just sketch it, on paper. Just do it by hand. I can do it exact if I do two reflections, flipping it left and right, and then flipping it up and down is exactly the same as rotating it 180 degrees. Yep.
So basically, you're just removing the arrow from one side and putting it on the other.
Yeah, that's negative w. Yes, other questions?
I was gonna say if you could just well, basically what you said.
All right, now just add them up. Take v and add negative w, which is really doing subtraction. All right, and then draw your final answer. Close enough. That's your answer, v minus w. So a new magnitude and a new direction. It's a new vector. Questions on that? Yep.
For the test, how close do we need to be to get the answer right?
Within a picometer. It'll probably be something where it'll snap to what you need
Oh,
to.
okay.
Yeah. So it'll automatically, it'll get it. Or if it's not something where you're drawing it by hand, then it'll be a multiple choice.
Oh.
Yeah. No picometer precision. Okay. All right. Let's look at this one. Okay, scalar multiplication. First, let me explain what that is. Okay, so we already know a vector plus or minus a vector is a new vector. This next thing we're going to look at is a type of multiplication, but it is not a vector times a vector. Okay, we're going to save that for Wednesday. It's going to be a number times a vector. We want to see what's going to happen. So what's an example of a number times a vector? 3v. That's called scalar multiplication. What do you think the 3 is going to do? Yeah?
3 times the vector.
Right. It's going to basically, if this is v, it's going to take 3 of those, and it's going to stack them together. So what kind of answer do you think I get when I take a vector and I multiply it by a number? Yeah?
So if number was x, it'd be xv. So like 3v. So it'd just be number and vector together.
So what kind of answer do you think that would be?
What's the word? I can't remember the term for it.
Well, I'm thinking of the description of it in terms of when you multiply a number times a vector, do you get a volume? Do you get an area?
Oh, you get a vector.
You get a vector, yeah. You're going to get another new vector. So scalar multiplication leads to a new vector. The number that you multiply in front, that is called a scalar. Now, I did 3. That made my vector longer. What else could happen when you scale something? Yeah?
I think we probably already said this, but if you multiplied it by -3, then it would you would first switch the terminal and the initial, and then you would basically do the exact same for multiplying by +3, but basically
Okay,
what
so
we're
yeah,
gonna say.
a negative can flip the direction, and
And
there's
then-
one other thing that can happen.
Rotate it?
Yeah,
Make it smaller.
yeah, it could make it shorter. So the three things that can happen when you scale the vector, it can get longer, shorter, or it can reverse the direction. Nothing other than that can happen. Unless you scale the vector by 0, then you don't have a vector anymore. Well, you have the
So-
0 vector now.
Yeah.
Okay, the 0 vector is really
So-
the only vector that doesn't have a direction to it, and it also doesn't have a magnitude, like the 0 vector. It's kind of a special case for vectors. So if you scale, how would you shorten it? You'd scale by a number less than 1, 1/3, 0.25, okay? Something like that. All right. So we've got v is given to us. They want us to find 2v and 1/2 v. Okay, let's start with 2v. Without measuring, how can I get 2v exactly? Yeah?
Well, you can just call that
Yeah.
the beginning point with the terminal point.
Just make 2 copies of it. Stack them together like we're adding them. And now you just created v plus v, and that's 2v. So the answer would be what's in red right there. Now 1/2 v, I can't, without measuring, I can't really do that. There's nothing I have in this program that allows me to scale by 50%. So I just have to estimate it. 1/2 v, about like that. The important thing is it still points in the same direction, but now it's half as long. If that represented a velocity, what's changing from v to 1/2 v?
Reduction.
Can you be more specific? Yeah.
Oh, wait, in terms of velocity.
In terms of velocity, what would be changing?
So the speed of it.
The speed of it. They are traveling in the same direction, but one of them is now going half as fast. Yep. If it was a force, the force would now be half the strength. Right. Let's try this one. So we're going to find negative. You don't have to put the 1, but negative 1v, and then negative 1/3 v. Yep.
Multiple questions. One, can like do imaginaries ever show up in vectors?
Not that we're going to study.
Okay. Probably say. Let's see. Infinity, is that like ever gonna show up in, well, like obviously not what we're studying, but does the infinity vector have like a name or a special thing, or is it just?
Nothing I've ever heard of, because that would represent like something going infinitely fast,
Yeah.
or an infinitely strong force. So nothing practical that we deal with.
All right.
Yeah. Okay. So first thing, somebody describe to me how to get negative v from positive v. Yep.
Just switch the terminal and beginning point.
Yeah, I'm not going to do anything fancy with reflecting it this time. I'm just going to make it point the other way. Okay, so there's negative v. And how about negative 1/3 v? Yes.
It would be the same as negative v in the direction,
Mhm.
but it would be 1/3 of the distance.
Yeah, so I don't know if that's a great sketch, but yeah, it's about 1/3 as long. So if you stack 3 of them together, that would be the original length. Any question on that? All right, let's just do the second one. We don't have to do both. 2v minus w plus u. So in order to do this, you kind of have to think ahead a little bit if your graph paper is only so big, because you want to try to stay on the grid. All right. So V is up and to the right. Let's think about negative W. Okay, so negative W is going to be up and to the left, and U is up and to the right. So all these vectors are going up. So we should start down. We should start kind of at the bottom of the grid. We've got one going right, we got some right, and we got some left. So I would kind of start in the middle of the bottom. Okay. What's the first thing that I need to put on my grid? Yeah?
I do 2V first.
Yeah, we need 2V. So let's make a copy of it. I'm going to start here and there. Okay, there's 2V. What do I need on the end of 2V? Yeah.
W. Negative W.
Negative W. So let's put the negative W on there. And what about on the end of negative W? Yeah.
U.
Yeah, we need a plus U. Okay. So there's 2V minus W plus U. Now, just connect the start to the finish. And that's your answer. Okay, so that had a little bit of everything. We had to scale vectors by putting multiple copies together. We had to flip one of them around, and then we had to add them all up. Okay, any question on that one? Okay, so again, adding vectors, doing things visually is great. But we're going to start to now talk about some things that we don't need to do visually. First thing is this. When you write a vector, you put double bars around the vector. Those double bars mean magnitude. Okay, that means the magnitude. And if you drew it as an arrow, what specifically are you measuring?
Speed.
The what?
Speed.
How about, like, if you think of literally the arrow, what are you trying to find about that arrow? Yeah?
The distance.
Yeah, the distance, the length of the arrow. Yeah, trying to find the length of the arrow. And we'll talk more about how to do it tomorrow, but the idea is you had a vector like that, and you want to find the length of it.
Triangle.
You make it into a triangle, and then you do the Pythagorean theorem. You just need to know the horizontal and the vertical between the terminal and the initial points. Also, when you are finding the magnitude of a vector, it is a distance. Distance is always a positive number. Okay, so look at those two things, the magnitude of V and the magnitude of negative V. If you found both of those answers, what would be the difference between them? Yeah?
Negative and positive. Different vectors. So different like plus or minus.
No. Yep.
There's no difference.
There's no difference. This answer is exactly the same as this answer. Because when you're finding the magnitude, this is essentially saying, let's measure the distance between, say, the door and where I'm standing, or where I'm standing to the door. You're just measuring in a different direction, but it's still the same distance. Now, when we do find magnitude, if it comes out to a certain number, then it has a special name. When we talked about circles, we talked a lot about a circle that had a radius of 1. Does anybody remember what that circle was called? Yeah?
Unit circle.
Unit circle. So what do you think we call it when a vector has a length of 1?
Unit vector.
It's called a unit vector. There are 3 special unit vectors we're going to talk about. And their names are I, J, and K. We're not going to talk about them until tomorrow. That's why when you name a vector, don't use I, J, or K. Yeah.
I was just looking at the home again, and the question grade it says if B, E was I and plus B, then what is A and B called?
I don't think we've gotten there yet.
Yeah, I'm mentioning I and J, so.
Yeah, we're not at that point yet. But we will be. Okay, so any question on that definition? Unit vector. Right, and we can tell if something's a unit vector without drawing it. We can use Pythagorean theorem and just find the length of that. And that's what we're starting to get more towards. Okay, getting away from drawing it and looking at another way that we can represent vectors with just numbers and symbols. There are 2 notations that I know of to represent vectors without drawing them. The first notation our book calls an algebraic vector. It's the name of the notation. So an algebraic vector is represented with 2 angle brackets, kind of like a less than and a greater than. You put 2 numbers in the middle, and you put a comma. Let me go back to an example we did in the notes, and let me show you how you could write it as an algebraic vector. And then I think that'll make a lot of sense. Okay. So let me go back. So I need angle brackets, and I need 2 numbers with a comma between them. Let's look at this one. I can figure it out. So if I was going to write this vector, it would be 5. 1, 2, 3, 4, 5, 6, 7, 8, 9. That is the vector 5, 9 in that notation. And you kind of maybe saw what I did. I counted the horizontal, and then I counted the vertical. That's what these 2 numbers represent. It's the horizontal distance between the points, the x, and then the vertical distance. That's the y. It's basically the base and the height of a triangle. That's what those 2 numbers are. So A and B are what we call the horizontal and the vertical components of the vector. You can think of them as directions, like the vector 2, 3. You're going to start somewhere, and you're going to go 2 units to the right, and then you're going to go 3 units up. So A tells you left and right, it's horizontal. B tells you up or down. The positive and negative directions are just like you always would expect. Positive is right and up. Negative is left and down. So let's draw the point. Let's draw the vector 2, 3 on the next page. 2, 3. What did I say earlier about vectors that this notation or the notation when you draw it does not tell you? It doesn't tell you what? Yeah? It doesn't tell you anything about position. Okay? It's nothing about the position. It just tells you the horizontal and the vertical components. So if I want to draw the vector 2, 3, I could start there, and I could go 2 to the right and 3 up. That's the vector 2, 3. Or I could do it over here. 2 to the right, 3 up. Do it over here. 2 to the right, 3 up. Those are all the vector 2, 3. Where do you think the most common place would be to start from? Yeah?
Quadrant 1 or from 0.
Yeah, the origin. Yeah. So the origin is if you could pick anywhere to start from, that would be generally where you would start from. If you draw a vector and it starts at the origin, okay, there's a special name for that. It's called a position vector. So out of all the vectors I have up there, the only one that's a position vector is the one that I just made black. That's a position vector. The one that starts from the origin.
Wait, so are all vectors starting at the origin a position vector or not?
Yes. Any vector that has its initial point at the origin is a position vector. So the last thing we're going to look at is how could you convert one of these other vectors to a position vector if I only told you where it started and stopped. Okay, so let's look at the one we have. We could look at any of them, but let's look at the one in quadrant 3. Okay, let's get rid of these other ones. And let's write down the coordinates. Okay, that's as big as I can make the grid. Hopefully you can see it. What's the coordinates of where that vector starts?
5, 2.
5, 2. That's the start. And what's the coordinates of where it stops?
7, 5.
7, 5. And that's where it ends. Somehow, if I take the start and the stop point and combine them together, I can get the vector 2, 3. Does anyone have a guess how we could combine those start and stop point together and turn it into the vector 2, 3? Yeah?
Subtract.
So if you subtract the start, the end minus the start, 7 minus 5, do that for the x's, and then do the same thing for the y's, 5 minus 2. You can convert the coordinates into a vector. Now, I kind of made a point of saying end minus start. Does it make a difference if you do n minus start versus start minus n?
You know, just change the negative. Like,
Right, you would get negatives, which would mean you'd get a vector that points the other way. So doing it in the wrong order will give you the wrong answer. Alright, so to find a position vector, if you have a starting and a stopping point, if they name your points P1 and P2, and they don't tell you which one is which, you can assume P1 is the start, P2 is the stop. But in this case, I'm spelling it out. P1 is the initial, P2 is the terminal. To find the position vector, do the terminal minus the initial for the x's, and then do it again for the y's. I'll keep that up, and let's look at our last example. Okay, so find the position vector between the points -1, 2, and 4, 6. P1 is the start, P2 is the stop. Anyone think they could give me the horizontal? The calculation for the horizontal. Yep.
Horizontal's left to right, right, like the flat one?
Yeah, and the
Oh,
x.
So that'd be 4 minus -1.
So 4 minus -1. And can someone else give me the calculation for the vertical? Fix that. Yeah. 6 minus 2. Okay, so the final answer for the vector? 5, 4. That's the vector. Okay. Any questions on that? That's it. That's how you find a position vector.
The homework is like in the Schoology as normal, like it's still the PDF and we can still like do the view PDF thing, right?
Yes.
Okay.
Just like normal, the page is just going to look a little different in the formatting because it's from a different textbook. So the homework is 1 to 10 all. And then on the 14 to 22 and 26 to 32, it's the evens. But only do what I'm asking you on 26 to 32. Because the directions in the book won't make sense till tomorrow. Yes?
So we don't do 3?
You don't do 3?
Because 3 is V equals AI plus B.
Oh, I figured that out. It's the position ones. That is what he said for the position vectors.
Oh,
It's
that's
just
it?
it's horizontal and vertical.
Yeah, we can talk more about number 3 tomorrow if we need to. But yeah, I think that one, you could technically skip 3 and you'd be okay. But yeah, the answer I think is horizontal and vertical.
And yeah.